Hello students, welcome to lecture of Kinematics and Theory of Machine, and we are going to learn today acceleration diagram for any mechanism. Okay, myself Patel, and let's start this lecture. So, as you know that in a velocity diagram there are 2 points are there. First is the magnitude of velocity and second is the direction of velocity, because we learn the velocity in a vector form. Now when we are going to start the acceleration, you must know what is the acceleration. Acceleration is a change of rate of velocity with respect to time. But as you know that velocity have two components in a vector form. One is the direction and second is the magnitude. So during the analysis of acceleration in any mechanism, there will be two components. First is a radial component and second is a tangential component. Why there is a two components are there? Because as you know that rate of change of velocity with respect to time, but velocity have two components. One is a magnitude and direction. So rate of change of magnitude with respect to time and rate of change of direction with respect to time, and that's why we have to consider both component of acceleration. Okay, let's start. So as you can see on a screen, AB link is there, which is rotating with a omega angular velocity and alpha angular acceleration. Okay, with respect to A, B is rotating. Now we are going to consider both components. First is a radial component. As you can see, the radial component, which is a perpendicular to the velocity of particle at any point. So the direction of radial component is a perpendicular to velocity, means it is a parallel to link. So radial component always will be there in a direction of link, or I can say parallel to link. Okay, you can see here the ARBA means radial component of acceleration for B with respect to A. Okay, so there is a formula is there, which is you can see on a screen. The radial component of B with respect to A, you can write there angular velocity square into length of that link AB. But as you know that angular velocity is equal to linear velocity divided by length of that link. So you can write here radial acceleration of B with respect to A, you can write that velocity, linear velocity square divided by length of that link. Okay, now takes the second component, which is a tangential component. Okay, so you can see the definition: tangential component with the parallel to the velocity of the particle. So as you know, the tangential component will be parallel to velocity, means it will be the perpendicular to the link. So whenever we take the tangential component of any element, we have to take the perpendicular to the link. Same as in velocity, we take the perpendicular to link, and that's why tangential component of acceleration same as the velocity of any link. Okay, so you can see there is a ATBA, means tangential acceleration of B with respect to A, ATBA. Okay, and you can see the direction is a perpendicular to that link, or I can say parallel to the velocity. The formula for that ATBA is equal to alpha into length of link AB. Means alpha means angular acceleration. Okay, omega is the angular velocity and alpha you can see is the angular acceleration. Okay, now let's make the acceleration diagram for this one single link AB. So as you can see here, this A point is fixed and there is a turning pair between this fixed element and AB link. So this whole link will oscillate with respect to A. Now as you know that A is a fixed point, so first of all what we will take? A point, A dash. Take the A dash is a fixed point. In an acceleration diagram we take A dash, B dash and C dash. Okay, so let's A dash. Now as you know that radial component is a parallel to the link. Now we will draw the radial component which will be the parallel to the link, and notation you can see the A R radial component of acceleration of B with respect to A. Okay, why we have drawn this in a downward direction? Because remember that whenever you want to draw any radial component of acceleration, first of all remember that which point you have, A point is you have, and now you are finding the acceleration of B with respect to A, means direction will be in this direction. Okay, B to A. So you will draw this line in a downward direction, B to A, B A radial. This point we take as a X because it is intermediate point. Now it doesn't reach to point D right now. So intermediate point, let's take X. Now we will draw the tangential component of acceleration. As you know that it is a parallel to velocity, or I can say perpendicular to link. So you can see on a screen tangential component of B with respect to A. Okay, this will be drawn in a direction of velocity. Now this point will be denoted as a B dash, and we have to connect this B dash and A dash. Okay, so this is the final resultant acceleration of B with respect to A. You can see on a screen this last resultant vector is a final resultant acceleration of B with respect to A. Okay, so remember that the final acceleration is a resultant of, or a vector resultant of, radial and tangential component. There are some special cases are there. Let's understand that, and then we will go to the examples. Okay, let's start. So let's check this assembly. You know that it is a single slider mechanism, in that OB is a crank which is a rotating, okay, with respect to O, and AB is a connecting rod which connect the crank to piston A. So you can see here, now if the crank is a rotating, if any link in a mechanism rotating with a constant angular velocity, then tangential component will be 0. Remember that whenever any crank pure rotation is with a uniform velocity is there will be no tangential component. Okay, you can see the point at end of link which moves with a constant angular velocity has a no tangential component of acceleration. Okay, so remember that whenever the crank is given which is rotating and alpha is not given, means alpha means angular acceleration is not given, then remember that tangential component we will take 0, because tangential component is equal to alpha into length of that link. But when this alpha is 0, our tangential component will be 0. Okay, remember that. Now, second important point, which is for the slider. When the point or any element moves along the straight line, it has no radial component of acceleration. Remember that you can see this piston right now, which is sliding in this direction. Okay, so there will be no radial component because there is a no change in direction. It is moving in the same direction. As you know that acceleration has a two component, one is a radial and second is a tangential. Okay, and tangential component is a sign of change of magnitude, and radial component is a rate of change of direction. But when the slider is sliding in the same direction, there will be no change in a direction. So radial component in all example, radial component will be 0. Remember this point always. For any slider we will take the radial component as a 0. Okay, so these are the two very important points, all should remember this. Okay, first is when crank with a uniform velocity. What is meaning of uniform velocity? Alpha will be 0. So some student maybe think about, sir, velocity is constant, so why we take the acceleration? Acceleration has a two component, radial and tangential. But this crank is rotating at every point its direction. In this position, the direction will be in this direction, direction of acceleration in this direction. Let's check if the crank position change, the direction of velocity is changing at every point. So we will consider the radial component, but magnitude is a constant because it is rotating at the same RPM like 200. So tangential component will be 0. Okay, and we will consider only radial component. Okay, so calculating these types of example, we will make the table here, and it is very useful in calculating any example of acceleration. Okay, let's understand the table for acceleration. So you can see on a screen, if you want to find any acceleration from this mechanism, first of all we have to find how many links are there, and we have to make this type of table. Let's understand the table first. So there are the 5 columns is there. First is a link. So how many links you can see on in a screen? Check this. First is a OB, which is a crank. Second is a connecting rod. Okay, and this piston. So 3 links are there. Okay, so in a first column you will write the OB, AB and slider A. Now the length of the link. So in given data these lengths are given, so we will put the in a second column the lengths, and for slider there will be no length, so it will be dash. So as you can see table on a screen, so first of all put in a first column the number means name of the links OB, AB, slider A. In a second column you can see length of the link. So whatever the length given like 0.5 meter or 2 meter, put the value. Okay, and keep the same unit for all. So in a second column you will put the length of that link. In a slider there will be dash. Okay, now we will find the velocity of every element in a mechanism, and we will. So if you want to solve any example of acceleration, first you find the velocity of every element in a mechanism. Okay, after that, as you know, the radial component is a v square by L, means velocity square divided by L. So what we will do, we will velocity square divide by this link, so v square by L, and same we will do for the second link, v square by L. So but you can see here the 0 due to straight line motion. As you know that slider is moving in a straight line, so radial component for that will be 0. See, here will be 0. And you know that OB is a crank, so if the crank is rotating at a uniform speed, then there will be 0. But sometimes they say OB has a omega of this and alpha this, means some angular acceleration is given. So as you know that tangential component is equal to alpha into length of that link. So then we have to find the tangential component. Remember that. Then we have to find the tangential component. Okay, when alpha angular acceleration given for any example. Okay, now this in these two cell there will be always unknown. These two cell always be unknown because we don't know the magnitude. This magnitude always we find by the diagram, but the direction will be always, as you know that in a tangent the direction is perpendicular to link. Okay, and in radial component direction will be parallel to the link. Remember that the direction of this both component. Okay, that's it. Remember that radial component is a parallel to link, tangential component is a perpendicular to link. Value of radial component is equal to v square by L, and tangential component is equal to angular acceleration into length of that link. Okay, thank you.